Okay, in today's lecture, we're going to cover the first part of the section 6.2 material on line integrals. So the idea behind a line integral is it's sort of similar to integrating a function of 2 or 3 variables over some plane region or some solid region in space. But instead of integrating our function over a region, we're going to integrate over just a curve, either in the plane or in space. So let's see if we can introduce the definition of a line integral. So let's suppose that we have some smooth plane curve, let's call it C, which has parametric equations. X is given by x of t, and y is given by y of t for parameter values t ranging from a to b. Or we could equivalently express this curve by putting those parametric equations x and y of t into the components of a vector function r of t, where t still ranges from a to b. As we move through this definition, let me keep track of what we're doing in our geometrically in our figure below. So if we have a parameter interval for t from a to b, we can use these parametric equations, x is x of t and y is y of t, to define the points along some curve C, which lies in the plane. So for a plane curve, we have just parametric equations for x and y of t. Now, if we were to take a partition of our parameter interval, that is the t interval from a to b, by choosing points t0, t1, t2, up through tn that lie in the interval from a to b. So here, if we choose a as t0, and then t1, t2, and these different parameter values up through tn as a partition of my interval from a to b, this would determine a partition, let's call it capital P, of the curve C by points which we will denote as P sub I, which has components xi, yi, where xi is the value of x at the parameter value ti, and yi is the value of y at the parameter value t sub I. So for each of these t values that we had in our partition of the t interval, we can define some point along our curve for that corresponding t value. So this first point that corresponds to what we get when we plug in t0, we would call p0. When we plug in t1 for our parametric equations, we get a point p1. When we plug in t2, we get a point p2, and so on up through our last parameter value, t sub n, gives us a point p sub n, which would be the endpoint of our curve. So these points, which we are working with, P sub I, divide our curve C into n subarcs, and the lengths of these subarcs we will denote as delta S1, delta S2, up through delta Sn. So the length of this first subarc from point P0 to P1 would be delta S1. The length of the subarc from P1 to P2 will be delta S2, and so on up through our last one would it be delta Sn. We're partitioning our parameter interval, which gives us the partition of our curve into these subarcs. And what we're going to do from here is choose a representative point, call it xi star, yi star, that lies in the ith subarc. So within each of our little subarcs, we're going to choose some representative point. Let's call it x1 star, y1 star. In my second arc, I'll choose another point. Let's call it x2 star, y2 star, and so on. And then if I have any function, let's call it f, of two variables, x and y, whose domain includes points on this curve C. So that is if my function is defined for every point on that curve, then we can evaluate our function f at the representative point that we chose in the ith subarc, and then multiply by the length of that subarc. And we're going to form a sort of Riemann sum where we will take the product of the value of our function at our ith representative point times the arc length of the ith subarc, and then add up that product over all such subarcs. That is from 1 to n. So adding up over the little partition arcs that we subdivided our curve into. And now if we let this norm of p denote the norm of our partition p of the curve, if we denote this to be the length of the longest subarc, then to get a finer partition of our curve C, we would take we would allow the norm of this partition to approach 0, so that we're dividing our curve up into smaller and smaller little subarcs. So that allows us to then define a line integral. So here is our definition. If f is defined on some smooth plane curve C, which has parametric equations, x of t and y of t, for values of t from a to b, then we would define the line integral of the function along that curve as follows. So let's start with the notation. So we would have an integral with a subscript c, so c here is denoting the curve that we're integrating over, of our function f, which is a two-variable function if we're integrating over a plane curve, ds. So this is with respect to arc length. So here the fact that we were multiplying our values of the function at a representative point by this arc length, we are integrating here, we would say with respect to arc length. And this is defined formally as the limit of our Riemann sum that we formed above as the norm of this partition P approaches 0, provided that this limit exists. Okay, so this is our formal definition of a line integral over a smooth plane curve. Essentially what we're doing is we're adding up the values, all of the values of our function f of xy, where we're taking points xy that lie along some plane curve. So, as with most of the integrals that we've seen in our course so far, it is not very practical to evaluate a line integral making use of that limit definition that we defined on the first page. So instead, we have a theorem which allows us to evaluate line integrals in the plane in terms of a definite integral of a single variable function. So let's see how this theorem works. It says if we have a continuous function f over some plane curve C that has parametric equations x of t and y of t, or equivalently as a vector function r of t whose component functions are x and y of t, for parameter values t ranging from a to b, then this line integral of the function f over that curve with respect to arc length can be found by setting up an integral in terms of the parameter t. So here we will replace x and y with the parametric equations for x and y for points along that curve. So for any point xy on the curve, the x and y coordinates are given by these functions of t. So we'll replace our x and y within our function by those parametric equations of t. And then on the end, we have this differential of arc length, ds. Now recall from our work in chapter 1, we had seen that the differential of arc length for a parametric curve is given by the square root of the sum of the squares of the derivatives for our parametric equations, that is dx dt and dy dt, times the differential of t. Or equivalently, we could write this in a more concise vector form as the integral of our function f, where x and y of t are replaced by the values defined by this vector function, r of t. And then our differential of arc length is given by the magnitude of the derivative of that vector function r prime times the differential of t. So we're converting our arc length integral to an integral over the parameter t. And here, if our curve is defined for values of t from a to b, we're then integrating this expression over the t interval from a to b. So let's look at an example to see how we could make use of this theorem. In this next example, we are asked to evaluate the line integral of x times y with respect to s over the curve c, which we're told is the line segment connecting the point -1, +1 to the point 2, 3. So in order to make use of this theorem to evaluate a line integral in a plane, we need to find parametric equations describing our curve. So in this case, we have a curve C, which is a line segment connecting the point -1, 1 to the point 2, 3. So here we may, even in this first example, think about visualizing our line segment here. So in the xy plane, we're looking at the line segment connecting the point -1, 1 to the point 2, 3. So we would be looking at the line segment from, let's call it point A to point B, traversed in this direction. So I could use little direction arrows to indicate the direction that I'm moving along my curve. And this is the curve that we would call C. Now, in order to use this theorem, I need parametric equations for that line. So recall, to find parametric equations for a line, we need a direction vector for the line. That is a vector that lies parallel to this line. So to find that, we could consider the vector whose representation is from point A to point B. So here, a direction vector for the line is the vector, let's call it V, which would have the representation as moving from point A to point B. So to get the x component of that vector, we would take the difference in our x values. So 2 minus a -1 gives us 2 plus 1, and then 3 minus 1 for the y component. So we have the vector 3, 2 as a direction vector. So parametric equations for this line segment would be given by x equals my x naught value. So for the first point, we had an x component of -1 plus the x component of our direction vector 3 times a parameter t. And y would have parametric equation 1, that is the y component of my first point A, plus the y component of our direction vector, which is 2 times t. And to connect these two specific endpoints, well, the point where I started, -1, +1, that corresponds to a parameter value of t equals 0. So we'll start with t equal to 0, and then we'll move up to the value of t that corresponds to the point 1, 3, which would be a t value of 1. So we have a parametric equation, or parametric equations for this line segment, our curve C. So we can then make use of this theorem to evaluate our line integral. to evaluate the line integral of xy with respect to s over this curve C, we would make this an integral with respect to the parameter t over the interval from 0 to 1. And the function that we were integrating was x times y. So we replace x and y with our parametric equations here. For points along that line segment, x is given by -1 plus 3t times y, which for points on our curve is given by 1 plus 2t. And then the differential of arc length with respect to t is given by the square root of the sum of the squares of the derivatives of x and y. So here, x prime is 3, so we have the square root of 3 squared plus y prime is 2, so that gives us a 2 squared dt. So we can then just evaluate this resulting integral with respect to t. So here, this expression under the radical, we have the square root of 9 plus 4, or the square root of 13, and I can bring that constant out in front of this integral. So we have the square root of 13 times the integral from 0 to 1 of, if we expand this integrand that we're left with, we have 6t squared plus 3t minus 2t gives us 1t, and then minus 1, which we are integrating with respect to t. So we have the square root of 13 times the antiderivative for this function is given by 2t cubed plus 1/2 t squared minus t, and we're integrating from 0 to 1. So let's see what we have. Here we have the square root of 13 times 2 plus 1/2 minus 1, minus, when we plug in 0 for t, we have 0. So we are left with the square root of 13 times 3/2, or if we want to simplify a little bit, square root of 13 times 3 over 2. Okay. So we see, making use of this theorem, as long as we can find parametric equations that describe points on our curve, then we can make use of this theorem to convert my line integral to an integral of a function in the parameter t. So let's consider what we're finding geometrically here. What exactly does a line integral represent geometrically? So here, if we have a function f of xy, which is non-negative for points over our curve, then this line integral of our function f of xy over the curve C with respect to arc length represents the area of one side of, we can think of it as a fence or a curtain, whose base is our curve C in the xy plane, and whose height above a given point xy on that curve is the value of our non-negative function, f of xy. So here in our figure, if we have a curve shown here in red in the xy plane, then if we're evaluating a line integral of a non-negative function over that curve, well, we can think about the value of the function f as describing the height of some fence that lies above a point xy along that curve. And this line integral, well, we're adding up these heights of all of our points over this curve. So we're calculating the area of this, of one side of this fence or curtain that's shown here in blue. So that's one way that we can think about a line integral geometrically. So let's look at another example. In this next problem, we're asked to evaluate the line integral of x squared times y with respect to arc length over the curve C, which is defined to be the upper half of the circle of radius 2 centered at the origin. That is x squared plus y squared equals 4. So here, again, let's maybe visualize our curve. We're talking about the upper half of a circle of radius 2 centered at the origin. So here we have some semicircle of radius 2. And we want to integrate this function x squared times y with respect to arc length over this curve. So if I want to make use of that theorem that we had introduced before the last example, I need to find parametric equations for this curve. Now for any part of a circle, an easy way to parameterize this curve is by making use of polar coordinates. So let's start by saying here, if we're using polar coordinates, we could parameterize our curve. So let's say parametric equations for our curve C are given by x equals. So for a points on a circle of radius 2, if I use polar coordinates, x is given by r. So for a circle of constant radius 2, I would have 2 times cosine of theta, or here I'm going to use cosine of t instead of theta, so that I'm consistent with the notation I'm using throughout this theorem. And my y coordinate would be given by 2 times sine of theta, or 2 times sine of t. And let's think about the range of our parameter value t here. So to trace out the top half of our circle, we could move from theta equals 0, that is the point 2, 0, or t equals 0. And then we would trace out the top half of this circle in a counterclockwise direction until I got to the point negative 2, 0, which would correspond to a rotation of pi radians, or 180 degrees counterclockwise from that positive x-axis. So once we have these parametric equations for our curve, we can make use of our theorem. So here, to evaluate the line integral of x squared times y with respect to s over this curve C, we would convert this to an integral in the parameter t. So here, from 0 to pi, we have x squared. So here, squaring x gives us 4 cosine squared t times y, whose parametric equation was 2 times sine t, times the differential of arc length, ds, which is given by the square root of the sum of the squares of the derivatives of x and y. So here, derivative of x is negative 2 sine t. We're squaring that quantity. Then adding the derivative of y is 2 cosine of t squared, all under the square root, times the differential dt. So let's see what we get here. We have the integral from 0 to pi of, multiplying my first two terms, I have a constant of 8 times cosine squared t times sine of t. And then we have the square root of, if we expand this, squaring our first term gives us 4 sine squared t, plus squaring the second term, we have 4 cosine squared t. So under the radical, we have 4 times sine squared plus cosine squared of t, which reduces to just 4, or square root of 4, which gives us a constant 2. So taking my constant 8 that we already had out in front times the square root of 4, we have a constant of 16 times cosine squared of t times sine of t dt from 0 to pi. So to find an antiderivative for this function, we can make use of a substitution. If I let u equal cosine of t, then du is given by negative sine of t dt. So converting this to an integral in terms of u, well, let's change our limits of integration here. For our lower value, when u is equal to, when t is equal to 0, u, which is cosine of 0, is equal to 1. And when t is equal to pi, u is cosine of pi, or negative 1. And then we have a constant 16 times u squared. And now sine of t dt is the negative of du. So we have a du with a constant of negative 1 out in front. Or here we see that our limits of integration, we might want to reverse. Our lower limit of integration is larger than the upper limit. So if I reverse them, take negative 1 to positive 1, well then I need to get rid of this negative out in front. I take the negative of a definite integral to reverse the order for the limits of integration. And now I have a 16u squared du. So my antiderivative is 16 over 3 u cubed from negative 1 to 1. So that gives us 16 thirds times 1 cubed, which is 1, minus negative 1 cubed is negative 1. So since we're subtracting that, we get a plus 1. And altogether, we're left with 32 over 3. All right. So really, for finding these line integrals over curves in the plane, the most difficult part in some cases is to find the parametric equations. Once you find your parametric equations, you can use this theorem that we discussed to convert your line integral to an integral in terms of the parameter t, and then use our techniques of integration from Calculus 2 in order to evaluate that integral. Now, one thing that was a restriction from the first part of our definition for a line integral is that we needed our curve C to be a smooth curve. That is, it didn't have any sharp corners or any cusps along that curve. But we can now extend our definition of a line integral to integrals over not just smooth curves, but piecewise smooth curves. So the next thing we'll do is try to extend our definition of a line integral to piecewise smooth curves. So what we mean by that is any curve which could be considered as the union of a finite number of smooth curves. That is, our curve C could be made up of smooth pieces, C1, C2, up through Cn. And the line integral of a function f of xy over a piecewise smooth curve would then be defined by taking the line integral over each piecewise smooth piece, C1, C2, up through Cn, and then taking the sum of those values. So here, to illustrate this maybe a little better, let's visualize what we mean by a piecewise smooth curve. So let's say in the xy plane, we have some curve that's made up of smooth pieces. So maybe some parabolic arc, and then we have like a sharp corner. I've got a straight line segment at a fixed value of y for a little ways, and then I have a different line segment. And then this would be my curve C. Well, this curve is not smooth. It has these corners or sharp edges in it. where it may not be differentiable, but I could think about this curve as consisting of three smooth pieces: C1, the parabolic arc, C2, my horizontal line segment, and C3, this last line segment. And to integrate the line integral over that curve, I would integrate over C1, C2, and C3, and then take the sum of those values. So let's look at an example of this. In our next problem, we're asked to evaluate the line integral of x times y with respect to arc length s, where our curve C consists of two line segments, the first one from 0, 0 to 1, 0, and then the second from the point 1, 0 to the point 2, 1. So again, let's see if we can visualize our curve here. So here we have in the xy plane a curve which is first moving from the point 0, 0, that is the origin, to the point 1, 0. And then, so this is the first part of our curve, is this line segment along the x-axis. And then the second part of our curve is a line segment from 1, 0 to 2, 1. So from this point 1, 0, we then take the line segment to the point 2, 1. So we could think of this curve C as consisting of two smooth pieces, C1 and C2, these individual line segments. So in order to find the line integral over our curve C, that is the line integral of x times y with respect to arc length over the curve C, we would integrate xy with respect to arc length over the first part of the curve, C1, and then add the integral of xy with respect to arc length over the second line segment, C2. So to evaluate each of these pieces using the theorem that we had been making use of, we need to find parametric equations for these line segments. So here, let's say the line segments can be parameterized as follows. So the first one, let's call our curve C1, then we'll have a separate parametric equation for C2. So C1 is the line segment from 0, 0 to 1, 0. So I can describe that by a direction vector, 1, 0. So my x equation would be 0 plus 1t, and my y equation would be a constant 0. For any point on C1, my y value is always 0. And our x value, which was given by t, can range from 0 to 1. Now for our second line segment, C2, we have the line segment from 1, 0 to 2, 1. So it has direction vector 1, 1. And it's moving from the point 1, 0. So my x equation would be 1 plus 1t. My y equation would be 0 plus 1t, where t ranges from 0 to 1, so that we're moving from the point 1, 0 to the point 2, 1. So going back to our line integral problem, we have the line integral of xy with respect to s over the curve C, again, is given by the sum of the line integrals over these two piecewise smooth, or over these two smooth line segments, C1 and C2. So let's set up integrals for each of these. For the curve C1, our parameter integral, or interval, was given from t equals 0 to 1, and the function that we were integrating was x times y. Now, along that first curve, x is defined as t, so we have t times y, which was defined as 0. and then times the differential of arc length, which would be given by the square root of the sum of the squares of our derivatives. So in this case, 1 squared plus 0 squared dt. So notice that this first function, since y equals 0 on that curve, this product x times y is 0. So our integral over that first line segment, c1, is 0, since the y value for any point on that line segment was 0. And then we are adding, for the second curve, c2, our parameter integral is from 0 to 1. We're looking at x times y. So here we have x was 1 plus t times y, which is t, times the differential of arc length, which would be the square root of derivative of x is 1 squared, plus the derivative of y is 1 squared dt. So this expression under the radical reduces to root 2, which I can then pull out in front of my integral, and I have root 2 of the integral from 0 to 1 of distributing my t. I have a t plus t squared dt. So to find our antiderivative, we have root 2 times a 1/2 t squared plus 1/3 t cubed, which we're then evaluating from t equals 0 to 1. So we're left with the square root of 2 times 1/2 plus 1/3, which would be 5/6. So we have 5 root 2 over 6 for the value of this line integral. So we can now integrate these functions over not only smooth curves, but piecewise smooth curves. And to handle a piecewise smooth curve, we might have to split it up into line integrals over its smooth components. So let's look at an example of extending our definition to a line integral of a function of 3 variables integrating over a curve in space. So much like the theorem that we saw for line integrals of plane curves, we have a similar formula for evaluating a line integral of a 3-variable function over a space curve. So here's what it says. If we have a continuous function f on a space curve C that has parametric equations x of t, y of t, and z of t, or equivalently, it's defined by the vector function r of t, whose component functions are x, y, and z of t, for a value, a parameter interval from a to b, then to evaluate the integral of that 3-variable function over the space curve C with respect to arc length, we could transform it to an integral in terms of t. We would replace the values of x, y, and z in our function by the parametric equations for x, y, and z in terms of t, and then multiply by the arc length, the differential of arc length, ds, which for a function of 3 variables is given by the square root of the sum of x, y, and z, the derivatives of x, y, and z squared, times the differential of t, or in the more concise form, f evaluated at the vector function r of t times the magnitude of r prime of t, which would be the square root of the sum of the derivatives of x, y, and z squared. So let's look at an example of this. For our first one involving a space curve, we're asked to evaluate the line integral of x times y times z with respect to s over the curve C, which is defined to be the part of a helix defined by r of t is equal to 2t, 3 sine t, 3 cosine t for t ranging from 0 to pi over 2. So here we have some helix which is extending or spiraling outward along the x-axis. Its radius would be 3, since we have a 3 cosine t, 3 sine of t, so it lies along a cylinder of radius 3 centered along the x-axis. And we're looking at the part of that helix defined on the time interval from 0 to pi over 2. So let's see if we can convert this line integral to an integral in terms of the parameter t. So in this example, our space curve, this part of a helix, is given in this vector form, r of t. So to set up our integral in terms of t, we're going to make use of this second form for this theorem. So we need to find the value of our function f evaluated at points on this vector function, and then we need to find the magnitude of r prime of t. So let's start by finding r prime here. So if we differentiate this vector function, our first component is 2. The second component is going to be 3 cosine of t. And our third component will be negative 3 sine of t. So when we take the magnitude of this, our magnitude for r prime is then the square root of the sum of the squares of these components. So we have square root of 2 squared plus 3 cosine t squared plus negative 3 sine t squared. So we are left with the square root of 4 plus, now for the second two terms, we have 3 squared cosine squared t plus 3 squared sine squared t. So that leaves us with just 3 squared, or 9. So we have the root of 13 for the magnitude of r prime here. So let's set up our line integral as an integral in terms of t. So here we could pull out the constant square root of 13 that we pick up from the magnitude of r prime, and we're integrating over the t interval from 0 to pi over 2. That was given in the problem statement. And the function that we're integrating is x times y times z. Now here, x, or the x component of our vector function, was 2t. Y is given by 3 sine of t times z, which is 3 cosine of t, times our magnitude of r prime, which was the square root of 13 we pulled out in front, times dt. So let's see what we're left with. If we group our constants together, we have a 2 times 3 times 3, which gives us 18. So if I pull my 18 out in front of the integral with the root 13, we have 18 root 13 times the integral from 0 to pi over 2 of t times sine of t times cosine of t dt. Now, in order to find an antiderivative for this function, we'll need to use integration by parts. So here, let's choose part of this integrand to be u. Here I'm going to choose u as t, and then the rest of it is dv. So in this example, we would have sine of t times cosine of t dt. And to use the integration by parts formula, we need to calculate du, which would be 1 dt, and v. So here v would be the antiderivative of sine times cosine. Similar to what we saw in our last example, we could make a substitution where u is equal to sine, and we find that our antiderivative would be 1/2 of u squared, or 1/2 of sine squared of t. So our line integral of x times y times z with respect to s over the curve c, well, we had a constant out in front of 18 root 13 times, the antiderivative of this function, which using integration by parts is given by u times v, so 1/2 t sine squared of t, evaluating from 0 to pi over 2, minus the integral of v du. So we would have the integral from 0 to pi over 2, v times du, so that is 1/2 sine squared of t dt. So let's see what we get here. For this first term, well, we had our constant 18 square root of 13. When we plug in pi over 2 for t, well, sine of pi over 2 is 1. So we have half of pi over 2, or pi over 4, minus, when we plug in 0 for t, well, sine of 0 is 0. So we pick up just a pi over 4 from that first term. Now, to integrate a sine squared function, well, we have to make use of our trig identity. So we would rewrite this as the integral from 0 to pi over 2 of sine squared is the same as 1/2 of 1 minus cosine of 2t. And since we already had a factor of 1/2, this will become 1/4 of 1 minus cosine of 2t dt. So let's see what we have. We now have 18 root 13 times our constant pi over 4 minus, for the antiderivative of this function, we have t over 4. The antiderivative of 1/4 cosine of 2t would be 1 over 8 sine of 2t. And we're evaluating that from 0 to pi over 2. So let's see what we have. When we plug in pi over 2 for t, we have sine of 2 times pi over 2, or sine of pi, which is 0. So writing this out, we've got our 8 root 13 times pi over 4 minus pi over 2 over 4 gives us pi over 8. Minus, when we plug in 0 for t, we have 0. So we are left with, altogether, 18 times root 13 times pi over 4 minus pi over 8 is pi over 8. So we are then left with 9 root 13 pi all over 4 after simplifying. So this would be the value of that line integral of xyz over this part of our helix. So we can extend our definition that we were working with to line integrals of functions of 3 variables over curves which are defined in space. And we see from this first example, of course, since we're working with functions of more than 2 variables, we may get an integral that's a little more tedious to evaluate. So one application that we will talk about for a line integral is in determining the center of mass of a wire that has variable density and has the shape of a curve in the plane or in space. So this result will be described by the following theorem, finding the center of mass of a wire. So here's what this theorem says. If we have a function, rho of xy, which represents the density of some thin wire, which has the shape of a curve C at a point xy, so rho of xy is the density at a point on that curve, which represents the wire, then the total mass of that wire is given by integrating the density function rho with respect to arc length over that curve C, which describes the shape of our wire. And to find the center of mass of our wire, well, if it's a wire in 2 dimensions, we would have our center of mass would be the point x bar, y bar, where x bar is given by 1 over the mass times the line integral of x times the density function with respect to s, and y bar is given by 1 over the mass of the wire times the line integral of y times the density function over the curve C. Now, of course, we could extend this to a wire that has a wire in 3 dimensions. So if we had a wire in 3 dimensions given by a space curve, its total mass would be found by integrating the density function in space, that is the density function of our wire at a point x, y, z over the curve C. And then our center of mass would be a point in space where x bar and y bar are the same, but y, or our third component, z bar, would be then given by 1 over the mass times the line integral of z times our density function with respect to arc length over our curve. So let's look at an example of calculating the center of mass of a wire. So in this next example, we have a thin wire is bent into the shape of a semicircle, x squared plus y squared equals 9, where y is non-negative, so that is the upper half circle of radius 3, and its density at any point is given by y. So the density doesn't depend on x, it only depends on how far we are above the x-axis, that is y. So we are asked here to find the mass and the center of mass of this wire. So let's start by visualizing it, a little sketch of what our wire looks like here. It was the upper half circle of radius 3. And so this, our wire can be thought of as being modeled by some plane curve C. And its density increases as y increases. So for points that are higher along this curve, it has greater density than for points where y is 0. It has very little density there. So in order to find the mass of this wire, we need to evaluate a line integral of our density function. And to evaluate a line integral over a curve, we need parametric equations for that curve. So let's start by defining parametric equations for this semicircle. So here, I'll say parametric equations are given by, in polar coordinates for our curve C, x could be defined by 3 cosine of t. It's polar coordinates on a circle of radius r equals 3. Y would be 3 times sine of t. And t, to describe the upper half of this circle, could range from 0 to pi. That is a rotation from 0 radians to pi radians to trace out the upper half of this circle in a counterclockwise direction. So once we have these parametric equations for our curve, we're ready to find the mass of this wire that has that shape. To find it, we integrate over the curve C our density function, which was y with respect to s. So let's see what we have. Converting this to an integral in the parameter t, we are integrating from 0 to pi. Y is given by 3 sine of t, and then the differential of arc length ds is given by the square root of the sum of the derivatives of x and y squared. So here, for x, we have a derivative of negative 3 sine of t squared, plus for y prime, we have 3 cosine of t squared, all under the radical, dt. So here, our expression under the radical reduces to 9 sine squared t plus 9 cosine squared t, or just 9. So then taking the square root of 9, we're left with 3. So multiplying by our original constant out in front 3, we have a constant 9 times the integral from 0 to pi of sine of t dt, which is given by negative 9 cosine of t from 0 to pi. So that is negative 9 times cosine of pi is negative 1, minus cosine of 0 is 1. So we have negative 9 times negative 2, or positive 18 for the mass of this wire. Now, in order to find the center of mass, we can make use of these equations that we had for x bar and y bar. Now, if we're a little bit clever here, we can save ourselves a tiny bit of work. We notice that this wire is in the shape of an upper half circle. So the wire itself is symmetric about the y-axis. And our density function in this example was rho of xy equals y. It doesn't depend on x. It only depends on how far we've moved vertically. So since my density function is also symmetric about the y-axis, it follows that the x-coordinate for our center of mass must lie on that y-axis. Or our center of mass must lie on the y-axis, so the x-coordinate must be 0. So we could say here by symmetry about the y-axis, the x-coordinate for our center of mass, x bar, must be 0. Now to find the y-coordinate, y bar, we take 1 over the mass, so that was 1 over 18, times the integral over the curve C of y times our density function, which was also y, so we have y squared with respect to s. So setting this up as an integral over the parameter t, we have 1 over 18 times the integral from 0 to pi of y, which was 3 sine of t, quantity squared, times the differential of arc length, which is, again, the square root of negative 3 sine t squared plus 3 cosine t squared dt. So this expression under the radical, again, reduces to 9, so square root of 9 is equal to 3. And so let's see what we're left with. We have altogether a constant of 3, use a different color here, 3 squared, so 9, times 3, which is 27. And then if I pull that out front, I'm going to have 27 over 18, which gives me a 3 halves if we divide through by 9 on top and bottom, times the integral from 0 to pi of, we had our sine function being squared, so sine squared of t dt. And again, to integrate sine squared, we've got to make use of our trig identity. Sine squared is half of 1 minus cosine of 2t. So here, half of 3 halves gives me a 3/4 integral from 0 to pi of 1 minus cosine 2t dt. So we have 3/4 times our antiderivative would be t minus 1/2 sine of 2t evaluated from 0 to pi. So plugging in pi for t, we have 3 pi over 4 times sine of 2 pi, which is 0. And then we subtract what we get when we plug in 0 for t, which gives us 0 here. So our center of mass would be the point x bar, y bar, where we found by symmetry that x bar was 0, and our y value would be 3 pi over 4. So here we could check that that makes reasonable sense. If we were to plot this point in the xy plane, we have some point that's where x is 0, y is 3 pi over 4. So some point that lies here along our y-axis inside of that arc of our curve. So it seems like this is reasonable, that that would be the center of mass for that wire. Now in the next part of this section, we'll start talking about integrating vector fields over a curve and talk about some applications of the integral of a vector field with respect to arc length, or we can define line integrals of multivariable functions over curves with respect to xy or xy and z. So we'll see those definitions and the idea of the line integral of a vector field in the